we discussed the design of shafts. Okay, we started with the design of shafts, and we talked about the different uh, criterias that we use in shaft design and customize them for shaft design. So if we recall, we talked about stress concentration factor. Now, what is, as we described earlier, that since there are components that go on the shaft, and since the cross section of the shaft is not uniform, therefore there is stress concentrations at different portions of the shaft. Now, the thing is that finding the stress concentration factor is an iterative process. Why? Because the problem is that first of all, you should know the diameter of the shaft D at the place where you want to find out the stress concentration factor. And again, uh, from this D, you will be able to calculate the stress concentration factor, right? So, therefore, if we find out D, then our shaft design is done. So, therefore, we have to consider some value of stress concentration factor to come up with some initial value of the diameter of the shaft. Okay? Now, but the good thing is that uh, when we design shafts, we use very standard components. So even if we don't know the diameter of the shaft, we can still come up with the stress concentration factor initially. Okay? Um, and if you look over here to your right, you would see table 15-8, 15A-8, A15, 15-8, and this gives you the round shaft with shoulder fillet. Okay. Read the caption over here. Round shaft with shoulder fillet in torsion, and then it gives you where C is equal to D by 2, T naught is equal to TC by J, and J is equal to pi that by 32 D4. So for that fillet, देखिए यहाँ पे this fillet is given to you if you know the ratio of the R by D ratio, which is this R and this D, you can figure out the stress concentration factor for that D by D and the contour for the D by D ratio. So you can go ahead and find your stress concentration factor for this from this figure. Similarly, looking down A15-9, so there are tables over there. And again, it is a round shaft. ठीक है? For some R by D ratio and D by D ratio, you can go ahead and find your stress concentration factor from these figures. Now, um, looking over here for shoulder, a standard shoulder fillet for with R over D equal to 0.02 and some value of D, the stress concentration charts will tell you that it is a 3 for axial. Similarly, there is some stress concentration for bending and some stress concentration for torsion. So you can use initially these values, but again, what you would do is you would want to avoid stress concentration. For example, these are some techniques which can avoid, with the help of which you can get rid of the stress concentration in a shaft. For example, looking at this figure A, if you look over here, um, in figure A, when you switch from, okay, where does stress concentration occur? When you switch from large radius to a smaller radius, basically this portion has now stress concentration. When geometry changes suddenly, there is stress concentration. Therefore, what you would do is, in order to avoid this stress concentration, अगर आप यहाँ पे देखें तो there is an undercut given over here, right? So what does this undercut do is that it will change your stress lines rather than going and getting discontinued over here, right? It will go smooth like these, and therefore the stress concentration over there is reduced. Similarly, in this figure B, there is a shoulder relief groove given over here. This is the shoulder relief groove. So at the bigger diameter, you give this shoulder relief groove where this is the shoulder, right? So your stress concentration again will eliminate over here. Okay? We can also give large radius relief groove on the smaller radius. अगर आप यहाँ पे देखें तो this is again a large radius relief groove that will relieve stress concentration. So these are the the ways in which you can relieve your stress concentration in shafts. Now, uh, if we if we also see in shafts, you don't only use these relief you don't only use these shoulders, you also use like keys, right? Now, when you use a key, the key looks, a typical key would look like, key way would look like this in a shaft, right? And you mount um, your component on the shaft, for example, a pulley or a gear, right? So let's say this is a pulley that you mounted on a shaft. And what do you do is that you insert in a key over here, which has some length, width, and breadth. It depends what type of key it is. But this key is, let me just draw one type of key over here. You might have seen this, that you insert this along the shaft. Okay? So it goes in here and secure this pulley on the shaft, and it basically transfers your torque. So again, what we would do is that for keyways, estimate of the stress concentration for keyways regardless of the actual shaft dimension. As I said that initially, since we don't know the diameter of the shaft, therefore what we would do is we would use estimates, and those estimates are based on the standard sizes of the keyways and keys that you use. ठीक है जी. Assuming a typical ratio of R by D equal to 0.02, what it would gives us is the stress concentration in bending is 2.2, and the stress concentration in torsion is 3, and assuming that the key is in place, we have inserted the key. Now, retaining rings, we can also use again standard sizes. If the groove width is slightly greater than the groove depth, the radius of the bottom of the groove is around 1 by 10. These are standards of the groove width. And again, from figure A-13-16 and A-13-17, stress concentration typical retaining ring, again, as I said, standard rings is that you are for bending it is 5 and for torsion it is 3. So these are the values that you would use. These are estimated values, or these are initial values that you are going to use. But once you know the diameter of the shaft, then you cannot use these values. Then you will have to use actual values that pertain to the shaft. For example, यहाँ पे अगर आप देखें तो this is a table, and this table 17-1, it gives you the first iteration estimates of for stress concentration factors. For example, shoulder fillet है, right? Shoulder fillet well rounded sharp round है, या end mill key seat है. These are the stress concentration factors in bending, in torsion, and axial. But again, once you know the actual diameter of the shaft, यानी यहाँ पे अगर आप देखें, these factors are only estimates for the use when actual dimensions are not yet determined. But once you find your diameter of the shaft, do not use these values once you actually find the dimensions, or the dimensions are available to you for the shaft. ठीक है जी. So this was one of the things which is the stress concentration factor, which is in the formula for finding the stresses, sigma m, sigma a, or rather sigma maximum, or sigma a dash and sigma m dash. ठीक है जी. तो before we design, when we design the shaft, we are going to use these values to determine the diameter of the shaft, and once we find the diameter of the shaft, we can find the actual stress concentration factor. The next thing to consider in shaft design is the deflection considerations. Okay. When there is a shaft, what is going to happen is that no wonder that you are going to support this shaft with the help of bearings. We already studied bearings in the previous semester. So if you use these supports, what is going to happen to the shaft is the shaft is going to, have some deflection.
Bending, sir.
Yes. And when it bends, there is going to be some deflection. Why? Now, the thing is that this is a fact that there will be deflection, but how much is this deflection? Okay. Now, And how much is this deflection and how much is allowed? The thing is, what if this shaft, bends like this? Is it going to work? No. If it is out of the limit, it is not going to work. Therefore, we need to check the deflection in the shaft. So, the deflection of the shaft, both linear deflection and angular deflection, any, we have to check y and we have to check theta, both should be checked at gears, bearing locations against allowable values. And who gives you the allowable values? The allowable values are provided by the supplier or manufacturers. Okay? So if you look over here to table 17-2, what does table 17-2 say? Typical maximum ranges for slopes and transverse deflections. So these are from manufacturers. For example, if you are using a tapered roller bearing, the slope at that location should not exceed 0.0005. Well, it should be between the ranges 0.0005 and 0.0012 radians. If it is out of this range, if it is more than 0.0012, then your bearing is not going to work over there, or it is not going to work efficiently over there. Similarly, if you are using a spherical ball bearing, the slope should be between these values, and this is the recommended or the allowable slope. Now, for again a sample of the transverse deflection for a spur gear with P less than P less than 10 teeth per inch, you should not have a deflection more than 0.01 inches. Similarly, for a spur gear with P um, between 11 and 19, your deflection cannot go beyond 0.005 inches at that location. Okay? So what do we do? For example, you designed a shaft. Okay? And the shaft design, from the shaft design, you got some value. Let's say that you have some diameter that you came up with, right? Now, how do you know what you need to do is you need to calculate the slopes and the deflections at the locations where it is necessary. As we said, for example, when you are using bearings, you should calculate the slopes because the manufacturer gives you the slope at that position. And how would you do that? I already told you in your previous class, for example, this is a shaft. So wherever your bearings are, those are your supports. And let's say if there is a gear over here and a pulley over here. So what you would do is you would calculate, you will use the shear force over here. Excuse me. Hello?
Yes, sir, we
Are
are
you
here,
guys,
sir.
do you guys hear me?
Yes, sir, we
Yes,
can hear,
sir.
sir.
Yes, sir.
And
But we can't see the sequence, sir.
okay, do you see it now?
Yes, sir, we can.
Okay, so let's say that this is a gear and a pulley over here, And basically these are loads on the shaft, right? So what we do over here is that we will find out the shear force V. We will also find out the bending moment, which is your M, and then you will go ahead and find your deflection Y and your slope over here. Okay? So once you find these, you can check if your deflection and slope are according to the values that are given by the manufacturer. From this, when you find your M and T, you also use these for calculating the stresses, right? So from this, you calculate the stress. You find out if your shaft is safe in stresses, and then you move to your deflection and slopes. Now, let's say you calculated the diameter of a shaft, and that is your D, but when you look at the table, your slope is more than what you are looking for. So in that case, what are you going to do is this will become your old diameter. Let's say that in this old diameter, or the diameter that you just calculated, the slope or the deflection is more than the allowable. So what would you do is you will need to find out a new diameter. And how do you get that new diameter? I'll just put in the formula for that. Okay, you will take that d old and multiply it with your y old, the deflection that you got, divided by the deflection that is allowable, right? And multiplied by the design factor, and to the power 1 over 4. So this will give you a new diameter that is, this will give you a new diameter that is going to be a diameter which will not produce that much, which will not have that much deflection. ठीक है जी, समझ आ गई बात कि ये आपका जो न्यू डायामीटर आएगा, this is going to be your diameter that will fulfill the requirement for the deflection. ठीक है जी, the allowable deflection. Similarly, even if the slope is not working, so your new diameter for the slope will be your d old multiplied by nd, and dy by dx is slope basically. Yeah, the slope that you just calculated for the old to the power 1 over 4, and the allowable slope from the table, and the one that we just saw from the table. So these two formulas are going to be used to correct your diameter for slope and for deflection. Now, once you find the new diameter at any place, maybe you have a shaft that has not just one diameter, but the diameter has different sections. For example, let's just, for the sake of clarification, let's say your diameter is D1, D2, D3. So there are three sections in the shaft. So once you calculate this D new, you are going to, for whichever section you calculated it, you are going to see what was the factor that you multiplied this old diameter with, and you found out the new diameter. You have to multiply all the sections with the same factor so that your diameter increases uniformly. समझ में आ गई बात? Like for example, your D1 was 1 inch, your D2 was 3 inches, your D3 was um, 2 inches. So, and let's say that you will find that factor which will be your D new by D old. So you will, and let's say that is 2. So you will multiply this by 2. You will get how much? 2 inches. Multiply by 2, you will have 6 inches multiplied by 2, and that will give you 4 inches. So your new shaft will have these dimensions, which will have the allowable slope and the allowable deflection. ठीक है जी. Okay. Now, looking at the angular deflection, we know that theta is equal to TL by GJ. Agreed? From your torsional um, in solid mechanics, you know that theta is equal to TL by GJ. So, देखें, if we have different sections in a shaft, for example, this is one section in a shaft, another section in a shaft, and another section in a shaft. ठीक है जी. देखिए, when you apply torque, there is going to be some deflection in this portion, and let's call that theta 1. There's going to be some deflection over here, and that will be theta 2. Some deflection over here, and that will be equal to theta 3. So the total deflection, and let's call that theta, is going to be the sum of all these deflections, which will be theta 1 plus theta 2 plus theta 3. And I can write this as theta equal to the sum of theta I, which is TILIGIJI. So your TI will be T1 L1 over G1 L1 G1 J1 plus T2 L2 over G2 J2 and plus T3 L3 over G3 J3. Now, generally, when you look at the shaft material, the material will be the same material. So if the material is the same, then G is equal to G1 or equal to G2 equal to G3. Similarly, आपका जो J है, not J, sorry, आपका जो torque है, that also remains the same. You are transmitting torque with this shaft. ठीक है जी, no matter what the section is, your torque should remain the same. So T1 will be equal to T2 will be equal to T3. ठीक है जी. So with that, my theta will become the sum of since T is the same, therefore I will say take that out, and it will be T by G sum of the Li over Ji, because these are different. J is equal to pi by 32 D4, so that will be different for the different section. Similarly, the length is also different. L1, this will be the length of the second section, L2, and the length of the third section, L3. So these are different, but I can calculate my theta with this equation, which is equation 7-20. ठीक है जी. Similarly, you can have the torsional stiffness, and we know what stiffness is. Our equation for the Hooke's law, I would say that would become that T is equal to K theta. Okay? F is equal to Kx. So that will become T is equal to K theta, or we can say that K, which is the stiffness, is equal to T over theta. Okay. So this is just an equation from that if you have that if you have springs in series or springs in parallel, how do you add them up. But the basic idea is that your k is equal to t over theta, or your theta is equal to ti over ki. It depends on the section, which section you are talking about. And your theta is the sum of theta I. Therefore, your ti over ki for constant torque, theta is equal to t 1 over k. So you will add the k's over here to get the overall stiffness, and that is the torsional stiffness of the shaft. Okay. Now,